You are able to see this slide?
Yes, sir.
Okay. So last class we discussed about the multi-level converters and its PWM techniques. And today we will just see the few control in the three level. Plus we will start the transmission line modeling, and then we will discuss the compensation system. So this is, if you are seeing here, we have already discussed there is three level uh, uh, the synchronous link converter. We have already discussed this one, and we had a source here, and then this U1. They both are connected through a synchronous link. That's why this is called synchronous link converter, and it is bidirectional, but this is a three level. Okay. So two level I told you, and three level also. When your voltage rating is very high, then you go for three level converters. And this is very popular nowadays in the transformerless the transformerless grid connection, so solar grid connected system or integrated system. And these are the bidirectional power flow, and this we have already discussed unity power factor and reduced voltage strength and the power switch. And this is the additional feature as compared to two level uh, synchronous link converter. The power switch rating is very low, and there is a voltage low voltage stress. So if you see this controlling and modeling of this one is a simple circuit, like we have already I have given that paper also to you, that the gamma here in two level it is plus one minus one, in three level this is this, okay, or this one, the switching is here, okay, gamma is 1 0 minus 1. So I told you three level is plus VDC 0 and minus VDC, and that way this is for three level converter. And this is the control action, how it takes place in the hysteresis current control. These are the hysteresis band as delta I. Okay, so this is the hysteresis band as delta I, and this I is your hysteresis band by which you control your actual current within that band. Okay, that is called hysteresis band, where we control our current within that band. And K is the feedback gain, where you can play with the K to get the stability and to increase the performance of the system. Okay. So if you go for a higher power, for example, in Indian Railways, we use this type of utility friendly converters. Okay, if you go to Chittaranjan, as they use this converter particularly, that this is a synchronous. There are three voltage sources, VA, VB, VC, and fed through this inductor, and this voltage is VA, and this is VU1, U01, and similarly you have for B phase, and this is for C phase, and three leg for three phase. And especially here we use the this type of circuit we use in the very high power drives. If you go to especially to this hot strip mill, any steel plant, there is a hot strip mill. In that hot strip mill, there are big motors actually. The induction motor is the size of maybe at least 100 meter is the length of that motor itself, and big shaft, and those are the drives by parallel converters, and or by nowadays they replace the parallel converter because parallel converter reduces the reliability. So this type of three level multi level AC DC converter are used here, and after this then there is a DC AC converter. We, instead of this load, there is a DC AC converter, the three level, and this one, and this converter is, these are the, this is how you control in the similar way actually. The your here the triggering signals are 12 number of signals. You have to apply 12 number of triggering because each leg you have 4. In case of 2 level you have only 6 number. In case of 2 level you use it have 1 2 like this, the 6. Okay, in case of 2 level, and 3 level you have 12 number of control switches, a control signal you require to turn on and turn off this one. The main idea is the same, that the idea is same, that this DC link voltage, this DC link voltage should be constant first thing, and the voltage and here input current both are should be the sinusoidal and in phase. They both should be in phase. So that is the main purpose of this synchronous link converters. So similarly, you can model this one. We have already discussed the modeling part and the modeling of the power converters. So by using state space model, you can design that very easily, and that is why K is represented your A, B, C. Okay, and here K is represented A, B, C because 3 equation you will get, and from that 3 equation you can derive this equation, and then you can write down a state space model, and from there you can find out what is the closed loop control transfer function. From that transfer function, because I have already discussed in the control of the power converters, in that I have designed that how to design the PI controller, PID controller, and P controller. So similarly, the proportional controller or proportional integral controller or proportional integral derivative controller. So similarly, this is the transfer function. When you find out, you can easily find out what is the controller parameters. Okay, after that, you can easily control this. Okay, so similarly, it is like last we have the hysteresis band of delta I, and similarly it is turned on, and this is our control. Okay, you can see here we have 3 inductors. Okay, these are 3 line inductors, sometimes we call, and we have a 3 phase 3 level. Okay, 3 level means I already we discussed multi level. 3 level is more than 2, the 1 0 minus 1. Then this is the symbol for hysteresis current control. This hysteresis current control is a big theory topic, and maybe I will give you this some assignment and this one where you can design easily, and that converter also, whatever assignment I have given to you, and that same converter will work. That you can use this hysteresis current control. First, hysteresis current control having 2 loops. One is voltage control loop, another one is your current control loop. This voltage control loop and current control loop already we discussed in the this. So the voltage control loop means you measure the DC link voltage here and give a reference voltage. For example, in Indian Railway, we have 1120 volt. Okay, it's the DC link voltage. And in different metros like Calcutta Metro, is a 1200 volt DC, and the Bangalore Metro is 1160 volt. So this depend on the design. Okay, according to design we do according to power rating. So when you measure this voltage, you take this reference voltage and then you compare that this reference with the actual one. Okay, this is plus minus, like in your control block you give this is a reference voltage, and then you have this is a plus and this is minus, and this is your actual signal. Okay, and the same thing we used in a comparator op amp, and then this will give you the error signal, and error is passed through the error is placed in a PI controller, and PI controller will give you I IA magnitude, or IM it will give. Okay, PI controller output will give you IM. Okay, IM. Then we take three template. Three template means you have here Vm sine omega t. Okay, maybe just a minute. Here you get Vm sine omega t. Okay, when this Vm sine omega t you multiply by Vm, so you will get sine omega t. This you bring here and multiply with our reference signal, a reference signal after PI controller, maybe here. This is IM. You get the maximum here due to PI controller. PI controller output will give you the maximum current, and multiply by the sine omega t, Im sine omega t, you get Ia reference. So this is Ia reference, and compare with the actual current in the phase A. This is the phase A. So this is compared. Okay, this is phase A. Phase A is compared here. Okay, and Ia and phase A is compared, and pass through the hysteresis band, which our logic already we have seen that this, if the current or the reference current is this one and actual current is in a band, okay, like this. So if this is your band of the current. So if you see here, it is our actual current for one sample time, and your actual current is controlled in a band, and this band is called hysteresis band, and within this band you need to control that one, and that is why this is hysteresis current is not a fixed frequency switching technique, it is a variable switching frequency technique, and this hysteresis will give you the switching signal for this one. So this way, this the hysteresis current control is designed. Now, you see here, these are the parameters what we took, and these are the parameters, and you can simulate the similar thing. You can see that this is the line to line voltage, okay, and A, B, C voltage, and this is the DC link voltage is around 320 volt, and which is 330 volt is constant, okay, although ripples are there, and you can see that both current and voltage, they both are sinusoidal and in phase also, okay. So this way you can easily control the this you can easily control this one. So today I will give just a brief introduction to hardware also. Those who will do later, you can understand that what are the complexities. So I have shown you here. It is a multi-level converter. You can see below are the all IGBTs. Okay, and above is the control circuit to turn on the IGBTs, and here the power supply for this control circuit. Ah. So this way you can see that this is the your power supply to this control circuit, and this is the lockout circuit what we have here. Okay, so this is a compact design of a three-level converter. But when you design like this, what are the problems? The problems are that because this is the switching very highly, they may be 10 kilohertz switching frequency. So during that period, this switching frequency will create and the electromagnetic interference which affect on these circuits. So that is why sometimes, although you are giving a pulse to turn on the thyristor, it is not able to turn on that. So this is what this complete unit is. This way, it was not possible to. So you can see here that this in this design, you can see that these are the IGBTs. Already I have shown you. Each IGBT have two IGBTs connected in series. These are all bidirectional. There is a diode also across each switch, like this here also. So this one IGBT, you can see that these are the Mitsubishi made IGBT, and these are the clamping diode. I have shown you in the multi-level converter. These diodes are clamping diode, and these diodes are not rectifier diodes. You should just remember that these diodes are a fast recovery diode. There are three kinds of diode. One diode is your, we have already studied in the power electronics. First diode, one diode is called the rectifier diode or line frequency diode. In the line frequency diode, it is operated for 50 hertz, and you do not, if you data sheet, if you go through that rectifier diode, it will specify the power rating and voltage rating and current rating. Voltage and current rating they will give. But TRR or reverse recovery time is not mentioned in case of a rectifier diode because those are slow diodes. They use for rectifier circuits. Okay. The second one is our Schottky diode, and Schottky diode, although very fast, but the power rating is very small. So Schottky diode we use in very few applications like pulse transformer design and the pulse rectifiers. We use those type of devices. Then another one is fast recovery diode. So fast recovery diode are these diodes. Fast recovery diode, if you see this fast recovery, it will quickly, fast recovery means what you get. I think you, all of you must be knowing reverse recovery characteristics. So when you turn on a simple, you turn on a, turn on the turn off the thyristor, so you will see that the after you turn off, then it takes certain period of time. Okay. Yeah. So this was our reference 0. And when you turn off, this is my current. This is the current IA, anode current. And when you turn off this one, when you turn off, you will see that diode will, for some time, the power diode, it is not there in the signal diode where you are using for your amplifier circuit, communication circuit. Those are the simplified, the signal diodes. So they do not have any reverse recovery characteristics. But when power died, they have reverse recovery. And they are very, very crucial in designing a power converter. So this reverse recovery characteristics, this diode, you see, this diode took lot of time, is this time period, TRR, because when you turn off or reverse the voltage, that time you will see that in P junction there are residual charges, and in the conductor surface in the depletion region also there are a lot of charges which is not combined together, and they require certain period of time to recombine together, come to the neutral stage, and that stage is called the reverse recovery period. And the time required to neutralize this both these holes and they recombine with your electron, and then it takes some time, and that time is called recovery time, and the current at which it occurs, that is called reverse recovery current, and the this is called the reverse recovery. And this is what why it is important when you have a high frequency application. This is very important because your diode is not actually turned off, and you have started using something else and applying another pulse. That is why it is very, very difficult. So this is what a fast recovery time diode, which it will give TRR or reverse recovery time, it will be given around 0.1 microsecond. Okay, and in this diode only you will get the reverse recovery time is mentioned, not in other places. So TRR is 0.1 microsecond, and there are different companies, like I have used this one from Mitsubishi, Semicron, ST Microelectronics, the ABB, they are now design, Infineon. There are different companies, they will, according to that you design, we design. And second one, after this diode, you can see that initially we put this wires as a conductor, and this wire carries finite inductance. And this also, when you connect this wire, they create a surge inductance, because whenever you have an inductor and this wire is large inductor, and it is if you have a large inductor, you need to have protection circuit like dV by dt protection and di by dt protection, like that. So to cope up this one, so all these connections you can see, because of this wiring connection, this becomes very difficult for designing. And then we designed the multi-level converter based on, not based on the wire. We disconnected completely. This converter was rejected. Okay, this design is not at all possible for us to fabricate any multi-level converter, because it cannot even operate more than 50 volt, and there was a lot of problems actually. So then we designed a region to multi-level converter with the DC rate, what is the rating of the voltage, then semiconductor, then the device, and then heat sink 7-layer bus bar. Anyway, there are many things that this is the diode IGBT, all of you know this. And to design a, a converter which blocks voltage 500 volt, 36 ampere. So we use this IGBT of this. Okay, although this is very low rating and our IGBT are very high, because we are available during that period. Okay. So this anyway, these are the different design aspects. And then you have to design the capacitor. I told you capacitor, what we take as a simple thing is not as simple. I told electrostatic capacitors, the electrostatic resistance, they are different for all the capacitor. So you need to equalize these two. So how to equalize, like in case of thyristor, equalization we have already discussed in the power electronics. So similarly, you need a different type of breeder resistor to equalize this potential across these two. Means net impedance must be same so that it will charge. So this is the breeder reactor design, and then this was the complete data sheet of the design, and there are many switching laws, other things we discussed. And then thermal model also, this is the thermal model, because when a heat sink and power converter is connected and through Anna bond as one of the chemicals, we put that one, then that time there is a thermal conductance actually. So generally, these mechanical people, they study those who are those who are studying thermal engineering, okay, mechanical. But as a power engineer, we must also know what is the heat transfer capability. So this heat transfer is treated as a thermal modeling, and after thermal modeling, this is the heat sink, and then we design the. I told you when we use that is called the stray inductance. I told you, and this stray inductance required lot of overshoot voltage, EMI, efficiency will decrease. So many things actually. So that is why we designed this multi-level converter as a 7-layer converter. Okay, you can see this is a one layer. This is, you can see that I have given here. Layer 1 means one bus. Layer 2, this is second layer. It's connection between this and this. And third layer is this, and this is third layer here. And fourth layer like this. So this design, you can see that here. That this is our heat sink. These are IGBTs. Okay, all are IGBTs, and we have not taken any. You can see that this IGBT acts as a fast recovery diode. When you will short the IGBT gate, both the gate you short it and use it as a diode, it will work. So you have this is the 7-layer copper bar. You can see that this is the IGBT, which is, and this is 7-layer copper bar. 7 layer. Each layer is connected, and certain connections you can see. This is the Teflon rod, and from Teflon rod we design these knobs where it will only touch whatever layer it is required, not to all layers. So this is one of the unique design which it was built after so many consultation with ABB Switzerland, where and Bangalore, we designed this one. So this is how the design takes place, and this complete system, front end converter, and this is the logic how. Then another aspect of our hardware is that voltage and current sensor and the calibration of these two, which is a very important in a hardware circuit. So voltage calibration and current calibration, they both are taken. These are very important, and this way we did. So you can see that this is the IGBTs, and if you want to use as a diode, you can sort it. You can see that there is a, you can sort it. Okay, only you use the diode because it will match the characteristics of other device. Okay, and this is the fan where it will blow in the heat sink so that the temperature will come down, the thermal management. And you can see that each there is a copper 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 and the Teflon, there is a copper connection, okay, between different 7 layers. And this is you can see that one of the Teflon we made in the workshop, where some size is very big, some one small. So wherever it you can see that this is the Teflon. And this till today it is available. It is one of the best design, and till today, although many generation has passed, so it is designed in 2006. Till today they are using in IIT Kanpur. You can see that there is a connection. Direct connection means directly it is connected. If there is no direct connection, that is connected through these switches. Okay. So then anyhow, this is how we control this complete unit, and this way the complete this is the your uh, control signal, and this is your driver signal. It drives the IGBTs. So wherever it is connected, you can see that here it is connected. These two are two IGBTs, and this one is a diode. This one is a IGBTs. This one is a diode. This is a diode. So like that, it is designed, and these are the how the hardware. It takes very important crucial step to design everything, starting from the driver circuit to you can see that this the filter circuit, all the thing. The students they generally do this, and there are this is why this there are many design aspects in the hardware circuit, and you can see here this is the current sensor, this is a voltage sensor which is connected, and these are the different way, and these are the material what we use during that period, and okay. Now we will start from let me go to blackboard. Okay, so we will start today. I don't know whether I can mic. Just a
Good morning, sir. Can you share a full screen, sir? Like it's not showing full screen, sir. Means right now, sir. Means which you are.
Sir, I can't hear you.
So you're not audible?
Okay, now you can hear.
Yes, sir.
Okay, so many I want to teach in this blackboard. So I thought that and today let us start this one that till I bring that iPod that I'll just order. I don't know when it will come. So maybe tomorrow I'll arrange because the audio cable is very small. So tomorrow I'll arrange a big cable so that we can directly discuss in the blackboard. I want to discuss in the blackboard. Okay. So oh, it is showing like this maybe. It is reverse.